Okay. Okay, so we are recording the lecture here, and so what you learned in the last class, you learned about section 8.5. Section 8.5 was on power series, and what you looked at was series that have variables x in them, power series that are functions of a variable x, and you were looking to find intervals of convergence for those power series. For what values of x does the power series converge? That's your interval of convergence. And the intervals can be open on the left and the right endpoints. They can be closed on the left and the right endpoints. You can have one endpoint that's open, the other endpoint that's closed. So that was section 8.5. Now, section 8.6 deals with representations of functions as power series. So what you're going to learn now, and this is actually a very important day for you, is you're going to learn how we can express some functions as power series. Okay? You're going to learn how, in section 8.6, how to represent certain functions as power series. Okay, so let me give you a moment to copy this example down. All right, Esther, so yes, so let me make a note of that. All the late extensions should last until November 25th for all of your most recent homework assignments. So I will double check that. Thank you, Esther. Okay, so here we want to find a power series and interval of convergence for this particular function. The function is 1 over 1 plus x squared. Okay, so imagine being able to write a function as a power series. Okay, and then of course we need the interval of convergence for the power series, because the function, if we write it as a power series, we can only write it as a power series. I want to say this right. The function is only valid as a power series over its interval of convergence. Okay, so the domain, for instance, of this function is all real numbers. Okay, the denominator is never equal to 0 for any value of x. The domain is all real numbers for the function, but you'll see that the power series for this function, the interval of convergence is not all real numbers. So we have to think, how do we go about this? How do we go about this? And to show you this, I want to take a very simple example to help you understand the formula that we're gonna use. Okay, so may I go to the next page? Are we good? All right, all right. So take a look at this. What I'm going to do is I'm going to get to a formula. I'm going to get to a formula, that's going to help us write that function as a power series. But since you're just learning this material, I have to do a few things first. So remember, let's say I wanted to divide 2,475 by 5. Okay, how many remember doing division like this in elementary school? Sure. So, you know, you take 2,475 divided by 5. 5 goes into 24 4 times. 4 times 5 is 20. You subtract, you get a remainder of 475, but you only write down the 47. Okay. And then 9 times 5 is 45. 5 goes into 47 9 times. The remainders, you get a 45, and then you subtract, and now you have a remainder of 25. And then 5 goes into 25 5 times, and you subtract, you get a remainder of 0. Okay, so this is the process of division. This is the process of division. Okay, well, what we're going to do is we're going to take 1, okay, and we're going to divide that by 1 minus x. Now, of course, our example, we have 1 divided by 1 plus x squared. Okay, but we're not going to do that yet. What we're going to do is we're going to look at 1 divided by 1 minus x. And, you know, we know how to divide a number by a number. We know how to divide something by something. So we're going to use the same process to divide 1 by 1 minus x. And this is maybe something you've seen in pre-calculus. So let's divide 1 by 1 minus x. Okay, so we're going to use the same process that we used when we divided 495 by 5. Okay, I'm going to put the 1 here. Okay, and the 1 minus x on the outside. 1 minus x goes into 1 time. 1 times 1 minus x is 1 minus x. And then I have to subtract the 1 minus x from 1. Okay, well, that negative here, that negative distributes, right? So 1 minus 1 is 0, but then 1 minus a negative x is a positive x. So we get a positive x there. And then, how many times does 1 minus x go into x? It goes in x times, because x times 1 is x. But x times 1 minus x is x minus x squared. We subtract that part, and we get a remainder of x squared. And then how many times does 1 go into x squared? It goes into x squared times. And we continue the process. How many remember doing this in pre-calculus? This is something that's taught in pre-calculus when you deal with rational functions. Okay, Rodrigo remembers it, Michael remembers it, Kahindi, sure. Nothing new here, nothing new. But look what's happening. Look at our quotient here. When we take 1 and we divide it by 1 minus x, we get 1 plus x squared plus, and it continues. I mean, what would the next term be here? You know, what would the 4th term be in the quotient? Good, x cubed. What would the 5th term be? Good, x to the 4th, and so it just continues. So look at what we've done. We've actually shown here, that 1 minus x equals 1 plus x squared plus x cubed and so forth. But hey, that's a power series. that can be expressed as a power series. So 1 over 1 minus x, that fraction, that rational function, can be expressed as this power series. But we recognize that as a geometric series, right? This is just a geometric series with a common ratio of x. Okay. So 1 over the rational function, 1 over 1 minus x is equal to the power series where n equals 0 to infinity of x to the nth power. It's equal to this geometric power series. And it equals that when when the absolute value of x is less than 1, because a geometric series only converges when the absolute value of its common ratio is less than 1. Okay, are there any questions so far? All right, may I go to the next page? All right. Okay, so this means then that, again, we have a formula for 1 over 1 minus x. It's going to equal this power series, this geometric power series, over the interval of convergence when x is between -1 and 1. And that's nice. But I need something a little more general to handle the example that we have to do. I need to have a little bit more general formula. So what I'm going to do is I'm going to replace the x with an apple. Okay? An apple could be anything. It could be x squared, x2, it could be anything. I'm replacing, I'm going to replace the x with an apple. All right? I mean, think of it like this. Think of it like this. We have an established formula here. Okay? 1 over 1 minus x equals this geometric power series. So what if I then, could I use that formula to find the power series for 1 over 1 minus an apple? And the answer is yes. It would just equal the power series n equals 0 to infinity of the apple to the nth power, where the absolute value of the apple, because that's my common ratio now, is the apple. That's where the absolute value of the apple is less than 1. Or, equivalently, we can say that the apple is less than 1 and greater than -1. Okay, so let's make sure everybody's comfortable with that. Are there any questions at all so far? Okay, who's so far, and this is really the formula that we're going to be utilizing. Okay. But how many are so far reasonably comfortable? Reasonably comfortable. Okay, maybe give me a thumbs up. All right, Kahindi is. Eric, Rodrigo, Michael. Okay, Nabil. Okay, very good. Mohammed, many of you, that's wonderful. Okay, well, remember what we're trying to do now. We have the formula, the function 1 over 1 plus x squared. And we're trying to express 1 over 1 plus x squared as a power series, right? That was the example that we're trying to do. So, you know, I look here at this at this 1 over 1 minus apple, and I look at the 1 over 1 plus x squared. And I mean, I have to find the formula. You know, I have to find the, you know, the power series. But can I identify what my apple is? Okay, Kehinde says the apple is x squared. Okay, let's see if there are any other if there's any other inputs. The thing is, okay. So Kehinde, you were almost right. Cologne, that's right. The apple's going to be negative x squared because 1 plus x squared is the same as 1 minus a negative x squared. You see that minus there has to be here in our apple formula, the apple formula here. Maybe I'll call it the apple formula. In the apple formula, in order that's apple formula. That's not a very good R and M. We can do a little better than that. Hold on. We're going to make it good, class. Let me write it again here. Okay, so in my apple formula here, in order to identify what the apple is, I have this negative. I have this negative in front of the apple. So the x squared, okay, the plus x squared can be written as minus a negative x squared, and that's how we get the apple. Okay. Kehinde, you're good with that? All right. All right. So apple formula right there. All right. So let's go ahead to the next page and work out the problem now. So 1 over 1, that my function is 1 over 1 plus x squared, and I'm going to write that as 1 over 1 minus negative x squared. Negative x squared is going to be my apple. Okay. Well, in the apple formula, and I'll go back, in the apple formula here, 1 over 1 minus an apple is the power series that you see here, n equals 0 to infinity, of apple to the nth power. So my power series for my function is going to be the sum where n equals 0 to infinity of negative, the quantity negative x squared raised to the n power, because negative x squared is my apple. And keep in mind the interval of convert, because this is a geometric series, my common ratio is what? What is my common ratio here? What is the common ratio in that power series? in that geometric power series. We know not all series are geometric power series. This one is. What's the common ratio in this geometric power series here? Negative x squared. Good, negative x squared. That's right, Rodrigo. And so in order for the power series to converge, the absolute value of negative x squared, which is the common ratio, has to be less than 1. Well, that means x squared is less than 1 because, you know, the absolute value of negative x squared is positive x squared, and x squared is positive. And so x is between negative 1 and 1. Okay, so in pretty much most of the problems you're going to see in section 8.6, they're going to ask you to find the interval of convergence. Okay, or the radius of convergence. But to me, the interval of convergence is more important because that tells you the x values for which the function can be written as a power series. Now, we look at this power series here. We look at this power series and we say, okay, yes, we have a power series, but but it's not in a very nice form. So I'm gonna write the power series in a nicer form. Negative x squared is like negative 1 times x squared. Negative 1 times x squared raised to the nth power would then be negative 1 to the nth power times x squared to the nth power. This is, you know, you're using the rule that a times b to the nth power would be equal to a to the nth power times b to the nth power. Okay, and so the power series can be expressed this way, but I'm still not happy. It's not pretty enough for me. X squared raised to the nth power, this part here can be written very nicely as x to the 2nth. And now this power series is as beautiful as I can make it. It's as beautiful as we can make it. And I'm even going to write some terms of the power series. Why not? I'll write the first 5 terms of the power series. Okay, are there any questions so far? All right, may I go to the next page? All right. Well, so this means then, when x is between negative 1 and 1, we can take our rational function, f of x equals 1 over 1 plus x squared, and express it as this power series. Okay, so like for instance, if you wanted to find out what f of a half is, okay, f of a half. A half is between negative 1 and 1, all right? And we know that if we were to just evaluate the function at x equals a half, it would equal 1 over 1 plus a half squared. okay, which incidentally is 1 over 5/4. So half squared is a fourth. 1 plus a fourth is 5/4. And that'll get you 4/5. Okay, so our function of f evaluated at x equals a half is equal to 4/5. But also, we could say f of a half will equal 1 minus a fourth. Let me kind of separate this. Okay, f of a half will equal 1 minus a fourth, because if you put a half in here for x, a half squared is a fourth. Okay, what would the next term be? Good, a 16th. That's right, Rodrigo, because if you put a half in for the x here, 1/2 to the 4th power is a 16th. Okay, then what's the next term? The next term's negative. What's the next term going to be? 1 over 64. Good. Okay. And keeps going, keeps going, keeps going. One moment, class. And you recognize this, incidentally, as a geometric power series whose sum is going to be equal to 1 over 1 minus negative a fourth. Because the A is equal to 1, and the common ratio R is equal to negative a fourth, based on this power series here. You know, if you look at the power series, or I should say just the series, it's not a power series because there's no variable x in there. But 1 over 1 minus negative a fourth, incidentally, that would equal 1 over 5/4, which is 4/5. You see how that works? So, of course, you know, for our, like, the average person, if they were to evaluate f of a half, okay, they would do it this way. They would just put the half in the function and get out the value. But now you know a second way to evaluate the function at x equals a half. You can use the function's power series to evaluate that function. How many think that's kind of cool? Well, I thought I'd be getting a lot of thumbs ups, you know, a lot of, like, you know, sometimes I get a lot of thumbs up at once, you know, but how many think it's maybe not cool, but interesting? I'll take interesting. Okay, thank you, Marcella. All right, thank you, Felicity. Kinda, Michael. All right, Rodrigo, Mohammed. Good, thank you, thank you. All right, let's look at another example. There are reasons. There are reasons why we want to express functions as power series. The last two examples I'm going to show you will show you why. It ultimately has to do with integration, but we'll get there. Let's look at a second example. Okay, let's look at this example here. All right, let me give you a moment to copy it down. Okay, so here we want to find a power series and its interval of convergence for this function here. Now this function is equal to x cubed over x plus 2. Again, another rational function. Okay. And all right, so, well, we have to use our Apple formula. We remember the Apple formula. So I'll take you through the solution. Are we ready to go to the next page? Okay. All right. Well, so what I'm going to do is I'm going to write x cubed over x plus 2, that rational function, as x cubed times 1 over x plus 2. Okay. Okay, and I remember here that 1 over 1 minus an apple let me just write my Apple formula up here. Hold on. Yeah. 1 over 1 minus an apple is equal to the sum where n equals 0 to infinity of the apple to the nth power Now let me ask you, this formula that I've written, is this correct, the formula, the Apple formula that I wrote there? Felicity says yes. Okay. Candy says yes. Let me ask you this. Okay, is there anything missing? Is there anything missing? Ah, that's right, Cologne. We need the interval of convergence. The interval of convergence says that the absolute value of the apple is less than 1, right? Which that's another way of saying, so what I'm trying to say is it's like when you buy a new car, you get a guarantee on the car, right? Well, we have a formula here. We have this apple formula, but we need to, what is it guaranteed for? What is it good for? It's good so long as our apple, when we identify it, so long as our apple, the absolute value of apple is less than 1, or that's another way of saying that the apple is between -1 and 1. Okay, very important to have the interval of convergence. Okay. So, okay, now I write x plus 2 as 2 plus x. In my f of x now is equal to x cubed over, f of x is equal to x cubed times 1 divided by 2 plus x. But I need 1 minus an apple in the denominator. So I got two problems here. I have a plus x and I have a 2. I need a 1 there. I need a 1. Well, I can manipulate this function. I can factor a 2 out of 2 plus x. I can factor a 2 out and write the 2 plus x in the denominator as 2 times the quantity 1 plus x over 2. Are there any questions on that? Okay, well now at this stage, am I happy? Am I happy right now oh well, and if you don't mind, all that 2 here, I'll put it under the x cubed. Okay, so am I happy now? Can I use my apple formula yet? Okay, that's right, Mohammed. I need a minus there. So I will write 1 plus x over 2 as 1 minus a negative x over 2. And now I can use the apple formula. Now I can use it, which is what I do here. Now please let me know if you have any questions. Is everybody okay with this part here? All I'm doing for that part is applying the Apple formula. And of course, I need to identify my interval of convergence. Well, the absolute value of the apple is less than 1. So like, well, I guess I could put in a few more details here. The absolute value of negative x over 2 becomes the absolute value of x over 2 is less than 1. And I can just write that as the absolute value of x over 2 is less than 1. And that then gets me down to here, where I have the absolute value of x is less than 2. Okay. So far, okay, we're right at this step, and that's good. But is the power series written this way? I mean, is it simplified? Is it simplified? Can we simplify that power series more? Well, we can, Kahindi. We can do something with that. Let me show you on the next page. It maybe looks like you can't, but watch. So this is where we were, right here. So f of x equals x cubed over x plus 2 is equal to, hold on here, let me make sure I got this right. It equals x cubed over 2 times the series, the power series, from n equals 0 to infinity of negative x over 2 to the nth power. But I can write the negative x as negative 1 times x. See that? I can write the negative x as negative 1 times x. And then that's raised to the nth power. I can break up this entire fraction and write it like this. Okay, and I get down to here. But I'm still not happy, because I have this x cubed over 2. I have this factor in front of the summation. I would like to have the power series written as the sum of, like whatever's in there. I don't want to. So can I bring this x cubed over 2, can I bring it inside the summation? Can I bring it inside the power series? Absolutely we can. That's right, Rodrigo, because this here, the power series, the sum is dependent on the, well, n changes, right, in the power series. I mean, n equals 0, n equals, you're adding up all these terms, an infinite number of terms, and to do that, n changes. But x is a constant in regards to the power series. I mean, x is a variable, but it's also you can treat it like a constant in terms of the power series. So yeah, we can factor in, bring in that x cubed over 2 in the power series inside the summation, and then I can write the power series in even in a prettier way. Okay, let me know. And then what I do is I write some terms of the power series. So like when n equals 0, you'll get this term. When n equals 1, you'll get this term. When n equals 2, you'll get this term, and so forth. Okay, so we recognize that our function, hold on here, you find it here. Our function, which was x cubed divided by x plus 2, we recognize that that function, well, is going to equal, and I can put it up here too, x cubed over x plus 2 equals our power series, but only for values of x that fall between -2 and 2. Okay, so like if you wanted to evaluate f of 3 using the power series, you couldn't do it. You can evaluate f of 3 by putting 3 in the original function, but you can't evaluate it with the power series. All right, are there any questions on that problem before we move on? Okay, Mohammed's good. All right, well, let's go to our, and incidentally, how many just sort of think that this is really beautiful math? How many of you think, I mean, I think it's like really beautiful math. It's so important too for your upcoming courses. How many, I mean, well, you said it's interesting, but it's important too to be able to express the power series in simplified form, like we're doing, because what's going to happen is in your web-assigned homework, there'll be a lot of multiple choice in there, and they'll give you answers that are in simplified form, and you have to find the right answer. But you're not going to get answers that like that there. It's going to be more like this here, in simplified form, and there's value to simplifying the power series. And I would want that on your next exam as well. Okay, let's go to the next example. Okay, give you a moment to copy that example down. Now, I should probably add a word here. Okay, we're going to do this. We're going to do this using differentiation. So this power series, or no, I'm sorry, this function, f of x equals x over the quantity 1 plus 4x squared. Because, I mean, would it be hard to use the Apple formula directly on that? In other words, so we're going to find a power series representation for this function using differentiation. I'm going to add those words. Looking at the right side of the function, what makes it hard to write that rational function as a power series using the Apple formula, like directly using the Apple formula? That's right, Michael, the square in the bottom. The square in the bottom. So because of that, what I mean is this exponent 2 here. That makes it difficult. So we're going to have to be a little bit clever here. So I'm going to show you what I'm going to do. Let me go to the next page. Instead of working with 1 over the quantity 1 plus 4x squared, I'm going to start off with 1 over 1 plus 4x. I'm going to start off with that. I can write 1 over 1 plus 4x as 1 minus a negative 4x, which gives me the series n equals 0 to infinity of the quantity negative 4x to the nth power, because that negative 4x is my apple. And then I can write that formula as the series, and hopefully I know there's a little bit. I think the writing's okay. It's but let me know if you can't read anything. But I think it's okay. Negative 4 times x to the nth power can be written as negative 1 to the nth power times 4 to the nth power times x to the nth power. Okay, because negative 4x quantity to the nth power is like negative 1 times 4 times x to the nth power. And that's how we get then this power series. And that's in the simplest form as it can be. Okay. And naturally, we always want to think about our interval of convergence. So because the absolute value of our common ratio negative 4x is less than 1, that means then that, well, absolute value of negative 4x is the same as 4 times the absolute value of x. So the absolute value of x is less than a fourth, and that means your interval of convergence is open interval negative 1/4 to a fourth. I will tell you in section 8.6, the intervals of convergence are going to be open intervals, because everything, all of what you're doing when you write the function as a power series, you're relying on that geometric series Apple formula. Okay. So this is nice. I've written 1 over 1 plus 4x. Okay. Okay, I've written that as a power series. But it's not the function I'm interested in. The function I'm interested in is x divided by 1 plus 4x quantity squared. But look what I'm going to do. I'm going to make use of this power series because I'm going to differentiate 1 over 1 plus 4x. Okay, that's the same as taking the derivative of 1 plus 4x quantity, the quantity 1 plus 4x raised to the negative first power. Using the chain rule, the derivative will be negative 1 times 1 plus 4x to the negative second power times 4, which is the same as negative 4 divided by the quantity 1 plus 4x squared. Let me give you a moment to, make sure you're able to, that you're comfortable. Okay, are there any questions? Any questions so far? All right. Well, so negative 4 over the quantity 1 plus 4x squared would be equal to the derivative of our power series, right? Because differentiating 1 over 1 plus 4x is the same as differentiating the power series of 1 over 1 plus 4x. And we established that the power series of 1 over 1 plus 4x is this power series where n equals 0 to infinity of negative 1 to the nth power times 4 to the nth power times x to the nth power. That's the power series for 1 over 1 plus 4x. And again, we're assuming that x is between negative a fourth and a fourth. So how do I differentiate a power series? How do I differentiate a power series? Well, I think you know if you have f plus g and you want to take the derivative of the sum, the derivative of the sum is the sum of the derivatives, right? So here, in my problem, in our problem here, right, we're taking the derivative of, I want to kind of highlight it in green here. We're taking the derivative of a sum. It's an infinite series, but an infinite series is a sum. So the derivative of the sum is the sum of the derivatives. So I want to make sure that you're okay going from this step to this step. Are there any questions on that going from here to here? You have to let me know. All right, well, so how do I take the derivative of negative 1 to the nth power times 4 to the nth power times x to the nth power? Okay, I mean, maybe I'll do a little aside here. How do I take that derivative? I'm taking the derivative of negative 1 to the nth power times 4 to the nth power times x to the nth power. How do I treat negative 1 to the nth power times 4 to the nth power in regards to x? Negative 1 to the nth power and 4 to the nth power are what? Those are treated as what in regards to x? Constants, that's right. Very good, Rodrigo, very good, Kahindi. Because negative 1 to the nth power and 4 to the nth power are not dependent on x. So I can just bring that constant out in front of the derivative. So I'm trying to justify this step here. I'm trying to justify this power series here. Well, the derivative of x to the nth, then, so like in this power series, negative 1 to the nth, okay, that makes sense. 4 to the nth, that makes sense. And then the derivative of x to the nth power would be n times x to the n minus 1. Right? That's what the derivative of x to the nth power is by the power rule. Okay, are there any questions on that? Okay, well, so now I want to do an erasure, but are we okay with so far? You have to let me know if you're uncomfortable. All right. Okay, and it'll be in the recording. Now look what we do next. Look what we do next. This power series here starts at n equals 0, right? And we are writing the power series, the same power series here, but we're starting it at n equals 1. The terms are the same, but we're dropping the term n equals 0 and going from here to here. Why can we do that? Just see who. Okay, just ignore that. It's like we're saying the first term of the series equals 0. Right? It's like we're saying the first term of the series equals 0. Well, the first term of this series does equal 0. Why? Why? Well, what is the first term? What is the first term of this series? Right, Michael, when n equals 0. So when n equals 0, the first term of this series here, and I'm trying to use arrows and circles because I know that you're probably going to be looking at this recording again. So look, when n is 0, you have negative 1 to the 0 times 4 to the 0 times n, but n is 0. See? So that all equals 0. That's why you can rewrite the series. Instead of starting it at n equals 0, you can start it at n equals 1. So the change of index is fine. But then look at what they do. Look at what they do. They write this series here as a new series. Okay, a new series. I'll put it in purple. This series here, where they're changing the index from n equals 1 to n equals 0. But in order to do that, what did they do with all the powers? Wherever you see an n, what does n get replaced by? Add 1, n plus 1. That's right, Michael. So, in other words, if n equals 1, like for instance, you would have here, you'd have negative 1 to the first power. Well, if you start at n equals 0, you want to have negative 1 to the first power in your first term, so you have to adjust the exponent by adding 1 to it. If you go down 1 on your index, if you go from n equals 1 to n equals 0, then all your powers of n have to, anywhere you see an n, you have to replace the n with an n plus 1. And so you get this formula. And this formula is actually, this formula here is actually, why would we do that? Why, you might say, well, why aren't we happy with that formula? Why do we gotta, rewrite it as this formula? It's because this formula looks a little nicer. Well, I want to be careful. The author thinks it looks a little nicer, okay? And the thing is, you have to be able to do that, because sometimes in WebAssign, when in your homework for section 8.6, when you look at when you have a multiple choice problem and you got to pick which one's right, sometimes it won't have your index. In other words, maybe they'll have answers where n equals 1, but the series won't match your answer, and so maybe you have to change the index. Okay. All right. Are there any questions on that? All right. Well, now we have a power series for negative 4 over the quantity 1 plus 4x squared. But remember, the original function that we had was x over the quantity 1 plus 4x squared. That was the function we had originally, right? But we have what we need. We have what we need to get it, because, so let me show you on this page here. So here's our function, x over the quantity 1 plus 4x squared. I'm going to write that as negative 4 over the quantity 1 plus 4x squared times negative x over 4. I mean, I can do that. I can rewrite my rational function as the product of two rational functions. We can do that. And why would I want to rewrite the rational function that way? It's because I know what the power series is for negative 4 over the quantity 1 plus 4x squared. I know I established that on the previous page. The power series is right here for that function. And then negative x over 4, I'll just put that right in front of the series. But I'm not done yet, because negative x over 4, I can bring that inside the summation. I want to write the power series as simple as I can. And you'll have a problem like this in your homework. Okay. Now, negative 1 to the x over 4 is the same as negative 1 times x divided by 4. So negative 1 times negative 1 to the n plus first power gives you negative 1 to the n plus second power. And then 4 here in the denominator, well, if you take 4 to the n plus first power and divide that by 4, you'll get 4 to the nth power. Okay. And then x times x to the nth power is x to the n plus first power. Okay, and so the x over one plus 4x quantity squared, okay, that is going to be equal to this power series. Got to be a little careful though. What do we need to add? What do we need to add to this statement? That's right, the interval of convergence. And what was the interval of convergence? What was x between? X was between a fourth, thank you, Cologne, and negative 1/4. Okay, let me know if you have any questions. Okay. How many of you are you, well, let me just see here, one moment. We should do one more. We should do one more example here. Okay, we should do one more. All right, but I mean, I'm gonna stop the recording here.